Hi, this is part 9 of chapter 3. In this part, we are going to learn about electronic configurations. Let's review what we did so far to come to this point of electronic configuration. In the last two parts of this chapter, we discussed about the quantum numbers and atomic orbitals. And we stopped our discussion with this slide, where it has all the information about what are quantum numbers, what type of quantum numbers are present, like principal quantum number, angular quantum number, magnetic quantum number, and electron spin quantum number. And when I finished my part 8 discussion, I finished my discussion with this chart, and I said you could use it as a reference to write the atomic orbitals of any particular element. And what we are going to do for electronic configuration is basically similar to what we just did here. And we are going to write it in a notation where you can easily read it. So let's go into this topic of electronic configuration. So electronic configuration basically describes how the electrons are distributed in various atomic orbitals. Atom has atomic orbitals now defined by the quantum number, and electronic configuration is basically the description of those electrons in different atomic orbitals. Now let's go into discussion with a simple example of hydrogen atom. So we know that hydrogen atom has only one single electron, and this single electron, according to that, I'm going to discuss rules soon, how you know that it has to be put in first. In general, low energy state is the first preference, but we go into extensive details after a couple examples, a couple simple examples. Hydrogen is the simple example. So it has one electron. How do we know? Because hydrogen has one proton. So for a neutral element, number of protons are equal to number of electrons. So the hydrogen first electron goes to the lowest primary quantum number, shell 1, and shell 1 will have one angular quantum number, L is equal to 0, so yes, so it will be 1s. And to show how many electrons are present in that particular orbital, you use the exponents. So principal quantum number 1, angular quantum number s, and the exponent 1 says that there is a electron in shell 1 subshell s. That is how we read the electronic configuration back. And when you have to show it in energy levels, you show 1s at the bottom in comparison to 2s and 2p. And this is how we are going to do. This is called electronic configuration, and this is the specifically electronic configuration of the hydrogen atom. Okay, so let's look into another example. Sorry, this is not another example. So it is a little bit discussion on low excited state and high excited state. If you guys remember, when we discussed about Bohr's model of hydrogen atom, we discussed the electron going from low energy state to high energy state and comes back and releasing photons during that process, right? So this is how this jump of electron happens. When hydrogen atom receives energy, it go to high energy state. That single electron go to there, either 2s, 2p, or maybe 3s, or maybe 4s, or maybe 6s, any one of those, or maybe 6d, any one of those. And when they come back, that is when the photons will be released and the radiation occurs. And this is how we read it, right? We discussed how these four visible lines came, and I believe this one is from N6 to N2, like some subshell in S get the electron when hydrogen is excited, and it returned the electron back to some subshell in 2. And this is from N5 to N2, this is from N4 to N2, this is from N3 to N2, emission by electron losing its excited state to the lower level state. Okay, so what we are saying is, because hydrogen has only one electron, the emission spectrum of hydrogen looks a little bit simpler compared to, for example, helium, which has 2 electrons. Helium has 2 electrons, so electronic configuration will be 1s2. When the helium gets excited, those 2 electrons will go to multiple places, and those multiple places, when it comes down, it will release multiple emissions. And as you can see, compared to hydrogen, helium has a little bit more dots, more regions in visible spectrum. That is why we said visible spectrum is a identity for each element, which is unique to the each element. So you can clearly differentiate hydrogen from helium to lithium to carbon to any element. And mostly we use it on metals like potassium, sodium. For all of these, you could easily differentiate one from another. So this we kind of already discussed it. Kind of to be specific, I kind of gave you a heads up in my previous part of the lecture when we said same energy levels will have same subshells, but I said that wait for the exception that we say. That exception is that within the same shell you will have different level subshells. Thus, it follows basically as S is in lower level compared to P, compared to D, and compared to F for the same shell. Sometimes there is another exception too, where higher level s orbital can sneak in inside because of its shape that we discussed clearly here. So as you can see it here, 1s has no issue, only one subshell, but 2s has subshell S and subshell P. So between S and P, according to this, subshell 2s is in lower energy compared to 2p. What it means is when you're trying to fill electrons, you go from bottom to the top, so you fill in electrons 2s first. That's why you need to know this chart of preference. And for shell 3, it has a 3s first, 3p, and 3d much higher. Between 3p and 3d, 4s sneak in. Again, s orbitals do that, bigger level, lower level orbitals do that, bigger shell, lower energy subshells do that. They kind of sneak in inside because they have a higher exposure to the nucleus protons because of their size, like smaller size. That's why 4s fills after 3p. And 3d, then you fill the 4p. And so you see the pattern here. Before 4d, 5s gets filled first. So you have 4d. And that is just one order. We are going to spend at least half an hour on this topic. So you would eventually, make connections what I'm going to talk about, because we are going to do a bunch of those examples right here in this lecture. All right, let's go. Okay. So when you write the electronic configuration, you would follow certain rules, and I'm going to tell you 4 rules in total. The first rule is that Pauli's exclusion principle. What it says is that no 2 electrons can have the same 4 quantum numbers. You should have at least one quantum number different from another. So principal, angular momentum, and electron spin, all of them cannot be same. If it is same, you're talking about some exactly same electrons twice, which is not possible. So let's say for 1s2, the helium element, let's talk about its quantum numbers. We know that 1 means shell 1, S means L is equal to 0, and S has no magnetic quantum number because L is 0, so M values are 0. So how do you differentiate these two? Because you have a same N, same L, same M. So to differentiate that, you would use the electron spin quantum number. 2 electrons, remember, one go up, one go down. Opposite directions they travel. Opposite directions they travel. That is how you will get 4 different quantum numbers. Because N is same, L is same, M is same, but electron spin quantum number once is +1, another time is -1. The one we write up, we call it as +half. The one we write down, we call it as -half. The second principle that we discuss is Aufbau principle. Aufbau principle says that electrons are added to the lowest energy orbitals first before moving on to higher energy orbitals. I kind of showed you a chart like 2 slides ago, like how 4s comes first before 3d, and also how 2s is lower in energy than 2p. how 3s is lower than 3p. That's what it says, follow this pecking order. There are shells, bigger priority, and within shells you have different subshells also will want to get filled first because they found to be at lower energy levels. So let's look into this example of lithium. So lithium has, if you look at the periodic table, you find that lithium atomic number is 3. So a neutral lithium electron should have 3 electrons. Now start working on electronic configurations with me. So by the end of this lecture, you will be fine on your own in writing electronic configurations. So if Aufbau principle says you should start filling up from the lowest energy levels first, and I showed you that 1s is the lowest, so you will fill the lowest energy completely, so 1s2 you will say, then you go to 2s. So in the 2s, out of 3 electrons you used for 2 for 1s, so you left with 1 more electron, so you write 2s1. So your electronic configuration going to be 1s2 and 2s1. That is the electronic configuration of lithium if someone asks you to write it. Let's look into another problem. Beryllium. Beryllium has 4 electrons. Again, practice with me. And Aufbau principle says that you should fill up the lower energy levels completely before you move into higher energy levels. Okay, so you start with 1s, and you know that 4 electrons, and for 1s you would use the 2 electrons, so you would left with the 2 more electrons. So those 2 more electrons should go into 2s completely, because according to the pecking order, 2s is in lower energy level, so you should completely fill it first before you go to the next subshell. Even if 2p also in shell 2, 2s is in relatively lower energy, so you should fill it first before you put electrons in 2p. So electronic configuration of beryllium is 1s2 and 2s2. Let's work on boron now. Again, write the electronic configuration with me so you can compare how you are doing. So boron atomic number is 5, so you should have 5 protons, so you should have 5 electrons, and you should start filling from the bottom. You'll put 2 in 1s, another 2 in 2s, just like how you did for beryllium in the previous example, and you still left with 1 more electron because 1s and 2s are completely filled. Now you can fill up the 2p with 1 electron. So if you write it in words, the code should look like 1s2, 2s2, and 2p1. That's the electronic configuration of boron. Let's look into another example, another principle, sorry. So the third important principle is Hund's rule. This is very important, and I want you to aware of it when you write the electronic configurations, especially in orbital notation. Hund's rule says that when you are filling up electrons, let me just read what it says, then I explain it in my own words. The most stable arrangement of electrons is the one in which the number of electrons with the same spin is maximized. Let me explain what it means is that, let's say if you have multiple number of orbitals in a subshell. So if you are trying to give electrons to multiple orbitals of the same subshell, you should look for ways to maximize the spin, like plus half, negative half, these spins. Should look for ways to maximize the spin rather than cancel it to make it lower. So in this example, let's look into 6. This is perfect example to discuss Hund's rule. So for boron, you said your electronic configuration is 1s2, 2s2, 2p1. In 2p1, if you count the electron spin, you end up with half 1, right? Up, 1 electron up in 2p, half 1. So for carbon, you have 1 more electron. The question is, where do you put that extra 1 more electron? Do you box it up in the first 2p orbital or do you put next to it? So let's see what Hund's rule says it. Hund's rule says that you should have maximum spin. So if you box it up, it is going to be negative half versus positive half. They cancel each other, become 0. But if you put in the next orbital of the 2p subshell, you're going to have plus half and a plus half. Spin is going to be plus 1. So it is the way to maximize the spin by giving the electron to next subshell rather than pair it already. That is what Hund's rule says. If you have to distribute electrons, distribute so that your spin is going to be maximum now. And we use the word degenerate to say that these are same level subshell orbitals. It's a science word. So what it means is same subshell orbitals. These are all degenerated p orbitals, which means they are all of same energy level. All right, so your electronic configuration is 1s2, 2s2, 2p2. Again, boxing this already with the 2 electrons is wrong because your electron spin will be 0 if you do that. That's why you need to put 1 here. Okay, it matters. For example, we are going to talk about topic called magnetism. Magnetism, this carbon shown to have single electrons, so it should have paramagnetic effect. If you box it up, it will have diamagnetic effect. So because it is proven to be that there were single electrons, carbon should have paramagnetic effect. I don't know if I have to correct it because we don't normally discuss for carbons, magnetism, we discuss for nitrogen, oxygen, fluorine. But I know I'm theoretically correct that single electrons are paramagnetic, paired electrons are diamagnetic. If I have to correct, I will correct later. So according to Hund's rule, let's work on nitrogen. Oh, I already showed you all of the work. So nitrogen has 7 electrons, so 1s2, 2s2, 3 electrons. If you put it in third box, you are maximizing the spin. So it is plus half now, another plus half now. 1 plus half, 2 plus half, 3 plus half, so overall 1 and half. So the electronic configuration is 1s2, 2s2, 2p3. Now, let's look into what happens if you start having more electrons. Like by nitrogen, you already completely half filled your degenerate orbitals of the same level subshell. Now you don't have to apply the Hund's rule anymore. So what if you have to work with oxygen? I already showed you again. What if you have to work with oxygen? So oxygen has 8 electrons. So you will fill 2 in here, 2 in here. You put first 3, 1 each in each 2p orbital. You're still left with 1. Then you can completely start pairing them, because you cannot put anywhere else, because you have to fill up the low energy orbitals according to Aufbau rule. You cannot go higher to maximize the spin, because the Aufbau rule says that first you need to completely fill before you move to the next energy level shell. Right? So electronic configuration will be 1s2, 2s2, 2p4. So again, if you have fluorine, fluorine has 9 electrons, so 1 more than oxygen. You already saw how oxygen is 1 paired electron. For fluorine, because you have 9 electrons, you will have second paired box in 2p. So your electronic configuration is going to be 1s2, 2s2, 2p5. Like I discussed previously about magnetism, magnetisms are 2 types, diamagnetic and paramagnetic. Paramagnetic is the word that we use for atoms with the single electrons. So they show magnetism, they respond to magnetism. If you have single electrons, they have a spin that they would respond to the opposite magnetism. In addition to completely filled electrons, which we call diamagnetism, they were not magnetically active. I'll show you that example in this slide. So neon has 10 electrons, so it is going to look like 1s2, 2s2, and 2p6. You fill the last remaining half-filled orbital of 2p. So your electronic configuration is going to be 1s2, 2s2, and 2p6. Now, Previously, I said that nitrogen, fluorine, and oxygens are paramagnetic because they have at least one single electron, so they respond to magnetism. But for neon, it has completely filled paired orbitals, which means they were called diamagnetic. In other words, they were not magnetically active because they have no single electron to interact with or to oppose or to get attracted. Single electrons, if it is positive one, will get attracted with the negative magnetism. If it is negative one, it will get attracted with the positive magnetism. But if they were all paired, they were all busy by themselves, so they will show no interest in magnetism. All right, let's summarize what we just did so far about electronic configuration. So these are the rules that you're going to use, and I hide this chart until now because I want you to get that knowledge that you need rather than the shortcut. You can always use this shortcut, but you need to know those Hund's rule, Aufbau rule, and Pauli's exclusion principle to have the understanding of why we do the things that we do in writing the electronic configuration in a specific way. But you can always use this shortcut. I'm going to explain how to use it. Basically, you follow the arrows. So, so the first rule of writing electronic configuration is you need to know that electrons will reside in the available orbitals of the lowest possible energy. How do you know which one is lowest possible energy is? If you write the chart by yourself like this, you can easily write like 1s first, 2s and 2p, then 3 has 3, 4 has 4, 5 has another 4 boxes, 6 has 3, and 7 has p. And if you like cross write like it is raining, we call it as like raining electrons from the top, it will give you indication of which is the preference orbitals, which is the lowest energy orbitals. 1s is lower than 2s, 2p is lower than 3s, and again come back here, 3p is lower than 4s, come back here, 3p is lower than 4p, 4p is lower than 5s. Starting here, 4d is lower than 5p, and 6s is lower than 5p. Come back here, 4f is lower than 5d, 6p is lower than 5d, 7s is lower than 6p. This is how we read it. You always fill the electrons from the top like it is raining, and these are the orders of the lowest energy orbitals. Okay? And remember, each orbital can accommodate only maximum of 2 electrons. Subshell S has 1 orbital. Subshell P has 3 orbitals. Subshell D has 5 orbitals. Subshell F has 7 orbitals. Let me just take a moment and make sure I write this one for you. Subshell S has 1 orbital. So 1 times 2 is, it will hold maximum of 2 electrons. Subshell P has 3 orbitals. P times 2 is 6. So P can hold maximum of 6 electrons. Subshell D has 5 orbitals. 5 times 2 is 10. So it will hold 10 electrons maximum. Subshell F has 6 orbitals. I'm sorry, 7 actually. Seven orbitals. So 7 times 2 will hold 14 electrons. So those are the maximum number of electrons each one of these subshells can hold. Different subshells has the different number of orbitals, thus they are going to hold different number of maximum number of electrons. So third rule is that electrons will not pair in degenerate same level subshell orbitals if an empty orbital is available. Basically, it is asking you to carefully follow Hund's rule. Hund's rule says that maximize the spin pair. One way you make sure that you are maximizing the spin pair is if there is an empty orbital, do not start paired. Make sure all of them are completely half-filled, then start paired so that you would follow this rule automatically. And use the chart. or remember how to do it, because they fill in this particular order because it is proven to be the order of lowest energy orbitals with experimental data support that we know currently that that is the filling orbitals energy levels. Okay, let's work on a problem. So the problem is asking us to write the electronic configuration and give orbital diagram of calcium. So calcium, well, it is generous that it already gave the atomic number, which is 20. So an element with 20 protons, an element with atomic number 20 will have 20 protons. So 20 protons will have 20 electrons. So let's work on the electronic configuration for 20 electrons. So let's see the plan. So now that you know that there are 20 electrons, these are the tools that you need to have. The chart of filling up electrons from low energy level to high energy level, and remember how many maximum electrons that you can fill in each of the subshell. Again, this is very important and you need to remember, and I showed you the work for it. And these are the maximum number of electrons each of the subshell can hold. F is 14. Okay, so 20 electrons means let's work on how do you fill the electrons. So in 1s you can put 2 electrons, right? And you completely filled it. And 2s has 2 electrons, and in 2p you can put 6 electrons because you have 20 electrons to work with. So you still only use 10 electrons. Then you fill it in 3s, so 2 electrons here. You used up so far 12 electrons. You still have 8 electrons, which means you can completely fill the 3p with 6 electrons. So far you used up 18 electrons. So which means you have 2 more electrons. S can take 2 electrons maximum. So 4s2. Now your electronic configuration is going to be, just read it backwards, 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. That is how you write the electronic configuration. Use the flowchart, you'll be fine. And you can actually draw the flowchart anytime with a little bit of practice. Whenever I require to write a flowchart, whenever I require to write any electronic configuration, just to make sure I'm not making any mistakes, I make my own flowchart and push the arrows, sliding arrows, then I tell the electronic configuration. Now, so this is the slide to, just to give you a perspective of low energy level and high energy level that I collected different models. So this is one way of remembering it. 1s, let me have a laser. So 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. Now you need to remember, so you could use it as a reference or you can remember. And this is the best method where you can write yourself, we call it as flowchart, and start filling electrons. And this to give another perspective of how to write the electronic configurations. Or you could actually use the periodic table to predict the electronic configuration using this model. And I think I have one more better explanation. Let me pause the video and let me show you the chart as well. All right, this is the slide I'm talking about when I said I had one more useful chart for you to use. This kind of replicate the periodic table. How this exactly looks like periodic table, if you can see it. It has group numbers 1A, 2A for the tall columns and 3A to 8A for the main group elements on the right side as well. And you can clearly see that the left side main group elements 1A, 2A has only s orbitals, s subshell orbitals, and the 6 main group elements on the right side has only p subshell orbitals, and all the transition metals has a d subshell orbitals. I shouldn't say, yeah, all the subshell orbitals has d orbitals. And these excluded inner transition metals are 4f and 5f has 4f and 5f. So you can kind of use it as a reference and predict the electronic configurations pretty easily. And these periods here are basically the shell numbers 1, 2, 3, 4, 5, 6, 7. So because it says 4 and 5, they fit in right after here and here. That's all for this part. I'll see you again in next recording.